Welcome back. Today we're going to be talking about Faraday's law. And that's also very much tied to Lenz's law. But first, let's talk about a law that we already know, Kirchhoff's law, and specifically his voltage law for loops. So here I have a ring of wire, conducting wire. And as you can see, we've defined voltage as the line integral, the vector line integral of E dot dr. So if we zoom in on a small segment, you'll notice that we have a dr, which is pointing in the direction of the segment itself, and then some E field, and that E field could be in any orientation. It doesn't even need to be constant. The point is that what we've decided is because electric fields are conservative, that means that if you travel around and come back to the same point you left from, that means that you did zero work. And that's similar with gravity, right? If I pick something up and then I drop it back down, I spent energy picking it up and I did work. And then I gained work back dropping it back down. So anything that moves and goes back to where it started from, the work done on it was, the net work done on it was zero. So electric fields are also conservative. And for that very reason, you'll notice that the way voltage is written is the line integral, vector line integral of E dot dr. And you'll notice that you rarely see the loop sign on the integral. You know, for a line integral, if you go on a total loop, you'll see something like this. And so the voltage going around the whole loop of E dot dr is actually equal to zero. And that's another way of writing Kirchhoff's loop rule. The way we learned it was using summation notation. And so the concept there is that, well, if I'm at point A and I go back to point A, well, 2 points can't have different voltages if they are in fact the same point. So in other words, you couldn't have A be 5 volts and 0 volts because it needs to be able to be determined. And so any 2 points that are at the same point must have the same voltage, which means that the difference between A and A must be 0 volts. Alright, so that's Kirchhoff's loop rule. How does this change into Faraday's law? Well, what happens is that it turns out Kirchhoff's isn't quite right. Kirchhoff's works if you only respect the electric field and we don't focus on the magnetic field. But the second we have some magnetic field B, all of a sudden Kirchhoff's loop rule isn't going to work anymore. And the reason why is because the change in flux of the B field with respect to time is actually going to induce another voltage, not just the voltage we had initially, but it will create another voltage. And so essentially, what's going on here is now there's another term, and we go ahead and move it to the right side. So now we say that the sum of the E dot dr's in a loop is no longer equal to 0 like Kirchhoff says it is. It's now equal to the change in the magnetic flux with respect to time. So this is our new term right there. And this can be kind of confusing because this is the change in the magnetic flux with respect to time, not just the change in B with respect to time, not just a change in the magnetic field with respect to time. So that means that if B is constant, like I have it drawn here, it just has 2 flux lines, we'll say. Well, then the flux wouldn't be changing with respect to time, because at 1 second there would be 2 flux lines, at 2 seconds there would be 2 flux lines. But what happens if at 1 second there's 2 flux lines, and then at 2 seconds there's 3 flux lines? Well, now we've had a change in magnetic flux. The flux has increased, and so actually an induced voltage will happen in this coil in order to to move current around and create an opposing magnetic field. So the current is going to try to oppose the increase in flux lines going down, and so it's going to induce a current that's going to go this way. And so essentially, this is very prevalent in science. The system is seeking homeostasis. So essentially, things don't like change in nature. You know, if you put your hand into water, you will create a divot in the water essentially, and the water will immediately go to try to fill up that divot. And in doing so, it'll probably overcompensate, and you'll get some waves. So this is very similar. If we try to go from 3 flux lines to 4 flux lines, the current will be greater in that direction. However, here's where things get a little weird. What happens if at second 1 I have 4 flux lines, and then at second 2 I only have 3? Well now the B field's flux is decreasing. And so, because the flux is decreasing, this current will now be going this way, because it wants to keep the B field where it was. And remember, the B field started with 4 flux lines, and then it dropped to 3. So now the current induced will actually try to add that 4th flux line back, and so in that case we'll end up with a current in the opposite direction as before. And I missed a term here. This is actually equal to negative change in magnetic flux with respect to time. The reason why the negative is there is to remind us that in whatever way the magnetic flux is changing, this term, this voltage induced, will actually oppose it. So, you know, if we try to go from 3 to 2 flux lines as time goes on, we will get an even bigger current trying to add those 2 flux lines back. So that's probably the best I can do at explaining it. I think the tricky part is that it's a change in flux with respect to time, not just the change in the magnetic field. So this right here is Faraday's law. And it tells us how a changing magnetic field can induce an electric field, and that's really important. This relation between a changing magnetic field and an induced electric field was known far before we knew that a changing electric field can cause a magnetic field. And so this was kind of the first relation that was found between the two fields. And so in the next video, I'll talk about the Ampere-Maxwell equation. And I hope this helps, and I'll see you then.